In the last lecture, we saw an array-based implementation of the union find data structure, in which the find operation took constant time, and we used an amortized analysis to claim that the union operation over a sequence of m unions would take m log m time. So effectively, each union was a logarithmic time operation amortized over the entire sequence. Now we will see a more sophisticated implementation which has even better complexity. So recall that the union find data structure keeps track of a partition of a set S and supports three operations. One is the make union find, which creates a trivial partition where each element belongs to its own, each element is in a singleton partition named by itself. So we use the same names for the partitions and the elements. So each S is in a partition called S, each small s. Find tells us which partition a given element belongs to, and union combines two components or two partitions into a single one. So the array-based implementation uses an array called component to tell us which component each element belongs to. It keeps an array of lists to tell us which elements belong to each component. So it's a kind of reverse mapping. For each component K, it tells us which members of the set belong to that. And finally, it keeps track of the size of each component because we merged components by taking smaller ones and relabeling them with the names of the bigger ones. So make union find was an order n operation, find was an order 1 operation, and the amortized complexity of the union operation was log m for a sequence of m operations. So we will now have a different representation. We will use nodes with pointers. Right? So each element of the set will now be represented as a node. The node will have two parts. It will have the name, which is the element that you're keeping track of, and a label part which keeps track of its component. Right? So it's a pointer to the component. Okay? Now remember that the names of the components are the names of the elements. Right? So if we have a name here, for example, we have a name J, it says that this node represents the element J, and its label points back to itself. So it says this is J belongs to the component J. Here on the other hand, we have the element I, and through this field we go to the first node which points to itself, and this said that I belongs to component J. So I belongs to component J. So we are we are making heavy use of the fact that the names of the elements and the names of the components are the same. So we are kind of, in some context, we are interpreting the name field as the name of the element, and when we are following pointers, we are interpreting the name field as the name of the component. So make union find is the initialization. So what it does is it will set up each component as a singleton containing an element of the same name. Right? So I belongs to the component I. So there is a node I which points to itself. Right? Then there is a node K which points to itself, indicating this is a component called K containing K. This is a component called J containing J. So we have n such components, 1 to n. So we have n such nodes, each of which contains the name in the first component and a pointer to itself in the second component, saying it's a singleton component. So after a period of time, we will see that when we merge nodes, these pointers will point, instead of themselves, it will point to other things. So here, for example, could be a component containing I, J, K and L. And the structure says that the name of the component is actually J. Right? So this is the component J, and it contains I, J, K, L. So you can see that the element I has a pointer not to itself but to another node. So if we follow this, we find that it's pointing to an element J which points to itself. So its name of the component of I is J. Similarly for L, if we start from L, L points to I points to J, and so on. Right? So we will see that this is how we will use to, this is the strategy we use to implement find. We have to start with a node and go up the path, and this will be a tree. So every path will end at the root, and the root will be the name of the component. So just to help us navigate this tree a little easier, let's assume that we have the following additional arrays of pointers and numbers. So we will keep track, first of all, of where each node is. Right? So we have an array called node here, and each element of the array is a pointer to the node containing that element. So the entry I says node I is here. Okay? Entry J says that node J is here, and so on. So there will correspondingly be an entry which says that node K is here, and node L is here, and so on. So every element in our actual set will have a pointer from this node array to the actual node in the tree where it, or the set of trees, the set of components, the actual node where that value lies. Then we need to know which are the components which are currently active. So here in this particular segment, ijkl, we said the component is j. There used to be a component I when I was initialized. There used to be a component k. There used to be a component l. But these names are no longer in use because these components have got merged directly or indirectly with j. So right now among ijkl, only j remains. Right. So we say that the root of j is the component j is the node containing j. And for all the other labels I, J, K, L, we say that I, K, and L, we say that there is no component called I, there is no component called K. So we just have a blank thing saying there is no root for these things. If you want to find the root of this component, go to the node I and then work your way up to it. Finally, we will use a similar strategy as before in terms of merging by size. So we'll just explicitly keep track of the size of each component. So here it says that the size of this component ijkl is 4 because there are currently 4 elements in it. Right? So we have this node pointer which points to each element in the set where it currently lies, which node contains that element. We have a root pointer which tells us for each component which is currently active in our partition, which is the root of that partition. And then we have the size which tells us the size of each component. So when we do union, we basically do this merging of the smaller one to the larger one, right? So here we have two components. We have component j, which is j, k, and m, and we have component I, which is I and l, right? So now we want to do the union of I and j. So now we first will we will have recorded that the size of I is 2 and the size of j is 3, right? So having recorded this, we have to now therefore merge I into j. So what this means is that this edge which says that I is the root of this string has to be destroyed, and instead we have to put a link like this and merge these two trees into one larger tree. Right? So if we do that, this is the resulting tree. Now we have a single component called j. Of course, we would have updated the size of j to be the size of I plus the old size of j. So now it will say 5 instead of 3. And notice that this whole operation is an order 1 operation because we take a fixed number of steps to find out the sizes of the two components, to find the roots of the two components, and to decide which root to massage into which other root. Right? So whether to make I point to j or j point to I. Right? So this is an order 1 operation. Okay? And that's because we have the size information to tell us the size. We don't have to go through the component to find its size. And we have this root information that directly tells us where the roots of the two partitions are. So we just have to go directly to that place and make one point to the other or vice versa. Now find, on the other hand, as we saw, requires us to start from the value that we want to check and work our way up to the root. So supposing we say find of u, then remember that we'll have this node array. Okay, and so node of u will say that the node containing u is here. So we will start there and then we'll follow this path. So we'll say, oh, this points here, and then this points here, and this points here. And finally, when we reach a node which points to itself, that is the name. So then we will say, therefore, that find of u is equal to j. Okay? So this takes time proportional to the path that we traverse from the node to the root. Now remember, initially, we had a path for u which looked like this. Right? So initially every node has a path of length 1 to itself, saying that it is its own root. Now why does this path change? It changes because of the union operation. Every time we do a union, one node which used to point to itself now points to another node, and everything below it has its path increased by 1. Right? So therefore the path increases by 1 every time the label of j changes. If we are going to go from find of j from j to the root, how much time this takes changes by 1 each time j changes its label. But as before, we are doubling the component size each time we merge. Right? So each time we do a union, the label containing j contains twice as many elements as it did before. Now finally, the best you can do is to combine all the nodes in your graph into a single component. Right? So the maximum component size is n. So therefore we start with a component of size 1, then we double it to 2, and we double it to 4, and eventually we cannot go past n. So this whole thing can be at most log n steps. So therefore log n times the label of j can change. Each time the label changes, because we take the root of another component and attach it here, the path length increases by 1. So the path length increases 1 plus 1 plus 1 log n times. So the path is at most log n. Okay. So with this analysis, we can see that because we are merging smaller components into larger components, find will take log n time. So we are now at a place where we are dual to the earlier data structure. In the earlier data structure with arrays, okay, so we had find was a constant time operation, and we had this amortized analysis that said that union was log n. Now we have this pointer based thing which says that union is order 1 but find is order log n, right? So it seems that we have got essentially a similar kind of structure, except that we have reversed the complexity of the two operations. Now it turns out that we can do something much more clever and actually make it even more efficient to find. So we can keep the order 1 of course for union, but order log n can actually be reduced. So the key is that once we have traversed this path from u to j, right, we know in some sense that not only do we know that the path containing the component containing u is j, we know the component containing l is j, we also know the component containing I is j. So why don't we make use of this information and not recompute it each time we come back, right? So what we will do is we will do the usual find j, right? So we will traverse the path and then we will go back from j to the root and say, okay, now I know this is j, so let me bypass this whole thing and maybe point directly to j. So I remove, okay, so I remove the earlier things. So I will remove this edge and directly go. Similarly, before I remove it, of course I'll go there, so I'll say I can remove this edge and directly go. So for each step I can remove until I finally reach the one which is just below the root. So basically now I will end up having a flat tree along this path. This path which used to look like this is now been flattened out like this. So everything now has a direct access to the path, right? So we are flattening the tree, right? So if you want to look at it pictorially, so I start with this, okay, and then if I look at the current situation, then I will replace this edge from u to l as an edge from u to j directly. Then I will replace the edge from l to I as an edge from l to j directly, and so now I end up with this flat tree. So now subsequent lookups are going to take only one step from u and l, right? So the first find takes log n time, then it takes constant time. So now you can actually show, I mean this is not an easy calculation, so we are not going to try and attempt it now. But after this you can show that just like we can do an amortized analysis for in the earlier array based implementation to get an overall log n, m log n cost, m log m cost for m union operations, here you can actually show that a total of n finds will actually take something almost linear in n. Now, almost linear in n is actually n times a function called alpha of n, okay, and this alpha of n is something which is the inverse of the Ackermann function. So the Ackermann function is something which grows very fast. Okay, so it is a function which grows faster than any exponential. Now this is like the log of the inverse Ackermann, I mean the log of the Ackermann. So you know that for the exponential function, the inverse is the log. So that's why log n is nice for us. It's slow, right? Log of 1000 is 10. Log of 1 billion is 20, 1 million is 20, log of 1 billion is 30. It grows very slowly because in the other direction it's growing fast. 2 to the power 10, 2 to the power 20, 2 to the power 30 grows very fast. So similarly, Ackermann grows very fast. So if you take what is the corresponding log function, for what value is this the Ackermann input, it grows very slowly. In fact, it is claimed that alpha of n is at most 4 for any value of n that you are likely to encounter in a practical computing problem that you can solve. Right? So you can think of this as being something like order n, because we know that alpha of n is less than or equal to 4. So this is like 4n. Right? So path compression gives us a drastic reduction from n log n, which we would get without path compression, to something which is linear. So therefore now by moving to this pointer based thing, we have actually achieved a considerable saving compared to the more direct array based implementation that we gave in the last lecture. So to summarize, if we implement union find using nodes with pointers, then we can do, of course, the initial setup, the make union find and linear time. Union now becomes an order 1 operation because we just directly access the two roots and merge the smaller root with the bigger root. And find, now if we use this path compression trick, although in principle it is n log n for n operations, it is n alpha n for n operations if we use path compression.